All right, let's get into it. We're opening up the case file on a galaxy called Messier 96. Now, on the surface, it looks like a pretty standard spiral galaxy, right? But buried deep inside are clues to a really unusual, maybe even violent past. So today, we're going to go on a cosmic investigation and piece together its hidden history. So here's our crime scene, if you will, the Leo I group of galaxies. And the first piece of evidence is this thing, a massive, ghostly ring of hydrogen gas known as the Leo ring. This thing is enormous. We're talking over 650,000 light-years across, just wrapping around these galaxies. Now, this is not normal. A structure this huge and well-defined doesn't just happen. Something big had to have created it, and we need to find out what. So let's profile the key players, our main suspects in this galactic neighborhood. We've got the big elliptical galaxy M105 at the center, and a couple of major spirals, M95 and our main subject, Messier 96. And while any of them could be involved, some early clues are pointing right at M96. Could this one galaxy really be responsible for that giant gas ring? Well, that's what we're here to find out. But hold on, before we start pointing any fingers, every good detective knows you have to establish the basic facts first. And in astronomy, the most fundamental fact of all is always distance. If we don't know exactly how far away M96 is, we can't accurately figure out its size, its true brightness, or its history. So how on earth do you measure the distance to a galaxy that's millions of light-years away? While we use this incredibly clever tool called the tip of the red giant branch, think of it as a perfectly reliable cosmic light bulb. See, in any old group of stars, the absolute brightest red giants all shine with the same maximum brightness before they fade out. So, astronomers use the Hubble Space Telescope to look way out in the galaxy's sparse halo, where there's no dust or crowding to mess things up, and they find these specific stars. By measuring how dim they look from here and comparing that to how bright we know they truly are, we can calculate the distance with amazing precision. And boom! The technique works. After carefully measuring those stars, we now know that Messier 96 is a confirmed 37 million light-years from Earth. Okay, that's a key fact locked in. Now our investigation can really start. With the distance nailed down, we can get back to the main event, connecting our prime suspect, M96, to that giant ring of gas. Is this galaxy the one responsible for the Leo ring? Well, this is where the plot really thickens. On the one hand, the evidence for a connection looks pretty solid. M96's outer disk is warped, its spiral arms are all lopsided, and it even looks like it's actively pulling gas right off the ring. That all screams past collision. But then, the defense steps in and says, not so fast. Those distortions could just be the galaxy doing its own thing, part of its natural evolution. And, for a ring that massive to form, you'd expect to see some really dramatic leftover signs of a huge collision. The evidence just isn't clear-cut. Oh, and get this, while all this serious investigation is going on, there's a much more distant galaxy, 2MFGC 8391, that is perfectly photobombing the whole scene. You can see it right there, a little edge-on spiral peeking through the faint outer arms of M96. It's just a great little reminder of how incredibly deep and crowded space really is. So the evidence in the main part of the galaxy is confusing, it's inconclusive. To crack this case, we have to do what any good detective does. We have to dig deeper. We're about to become cosmic archaeologists, digging into the oldest, faintest part of the galaxy, its huge stellar halo, where the real secrets are buried. So, astronomers aimed Hubble way, way out from the bright center of the galaxy. See those two little highlighted squares? We're talking about 50,000 light-years from the core, deep into the halo. The idea was to get away from the bright lights and the chaos of the galactic city and survey the quiet, ancient suburbs where individual old stars hold the real story of how this galaxy was built. And this is exactly what we call stellar archaeology. Every single one of those faint, ancient stars is basically a fossil, and if we can study their properties, their color, their brightness, and most importantly, their chemical makeup, we can start to piece together the entire construction history of M96, one star at a time. And here it is, our first big break. Each dot here is a star. The charts on the left are from those two spots in M96's halo. The one on the right, that's just a random, empty patch of space for comparison. Now look closely. See that thick clump of red giant stars on the left? Now look to the right. It's gone. That right there, that is the unmistakable fingerprint of the galaxy's ancient halo. We found it. Now for our number one forensic tool, metallicity. It sounds complicated, but it's simple. In astronomy, metals are just any element heavier than hydrogen and helium. The very first stars were made of basically just hydrogen and helium, so we call them metal poor. Every generation of stars after that is born from the recycled ashes of older ones, so they get more and more metal-rich. A star's metallicity is a direct clue to when and where it was born. It's like a birth certificate. So what did the forensics tell us about the stars in M96's halo? The number came back minus 1.36. Now, to put that in perspective, that means these stars have only about 4% of the heavy elements that our own sun has. They are extremely metal poor. This is a massive clue. Okay, it's time to put all the pieces on the board. We've got the mysterious Leo ring, the distorted disk of the galaxy, the confirmed distance, and now this incredibly metal-poor halo. It's time to piece it all together and deliver the final verdict on Messier 96. And this, right here, this chart is the smoking gun. It plots how massive a galaxy's halo is against how metal-rich that halo is. And normally, there's a really clear pattern. Bigger halos are more metal-rich. You can see galaxies like Andromeda and our Milky Way follow the trend perfectly. And then look at M96. It's not even close. It's a total loner, way, way off on its own. A dramatic outlier. So here's the bottom line. M96 has a pretty massive halo for a spiral galaxy, which is normal. But that halo is way, way more metal poor than it has any right to be. It completely breaks the rules for how we thought spiral galaxies were built. It has the body of a big galaxy, but the chemistry of a much smaller one. It's a true cosmic oddball. So how in the universe does a galaxy get like this? Well, there are two main theories. One is that really early on, M96 had one giant meal. It merged with and swallowed another big galaxy that happened to be extremely metal poor. The other idea is that it didn't have one big meal, but instead spent billions of years just snacking, slowly pulling in and absorbing a huge number of tiny metal-poor dwarf galaxies. And the researchers who cracked this case put it perfectly. They said that M96's entire life story, the way it was built, seems to be fundamentally different from every other spiral galaxy we've studied nearby. It just followed a different path. And really, that's the big takeaway from this whole investigation. We may not have definitively solved the mystery of the Leo ring, but in the process, we stumbled onto something even bigger. M96 is a genuine puzzle that is forcing us to rethink our theories about how massive galaxies actually grow and evolve. So this whole case leaves us with one final big question. M96 proves there's more than one way to build a galaxy. If it followed such a unique path, how many other strange and unexpected formation stories are still out there, just waiting to be discovered? And what hidden secrets about our own galaxy's past have we just not uncovered yet? The investigation continues.